Hello, my name is Stephen Morgan. I'm the Science Communication Outreach Officer for the University of Sydney Mathematical Research Institute. And I'm here today interviewing Dr. Nancy Scherich, Visiting Assistant Professor at Wake Forest University. Dr. Scherich was supposed to come to the Mathematics Research Institute. Unfortunately, that's been curtailed by the current COVID situation. So sadly, you're not able to join us at the moment, but we hope that you'll be visiting us after things have calmed down a little bit.
Me too.
But in the meantime, I thought that we could have a talk with you about your research and mathematics in your life, and just to let people know how those sorts of things work. So how would I start out by asking, what do you do your research in?
So my research is in sort of the intersection of two fields, algebra and topology. And I kind of think about various different types of projects, but most of them are in the field of knot theory, like K-N-O-T, knot theory, like tie a knot with a rope. And I think about braids, which are a specific type of configuration of a knot. And the various things I like to think about is how can you represent a braid in a more sort of mathematical, tangible way. So I would call that a representation. So you take braids and sort of change them into something else. And that something else I think about is a matrix. So that might be like a grid of numbers or a grid of polynomials. And that kind of feels a little more traditionally mathematical. So we can study these matrices as a way to study the braids. And that's kind of the foundation of the research I do.
So braids are a very concrete object that anybody who has hair or has a long string can actually play with themselves. What sort of questions do you answer about braids?
That's a good question. So a lot of the properties about braids that we care about are, or that I care about, are sort of, can we faithfully represent braids in this new format, these format of matrices? So what does that mean? What is a faithful representation? So braids have a mathematical structure to them. So if we're thinking about braids as like ropes in the air that are tangled and tied up, and they start at the top and they tangle and then they end at the bottom. You can make new braids by taking two braids and then stacking them on top of each other. So you can make a longer braid. And there's certain properties that happen within these braids. So sort of if you allow the strands to blow in the wind, the crossing information and the way that it looks might change, but we still have the same braid there, just might have a different sort of configuration that you blow on it. And so these types of properties that we're looking at are algebraic properties of these objects, of these braids. And so to say we have a faithful representation is to say that all of these matrices that we're dealing with capture all of the properties of the braids that we started with, just sort of in a new format. And every braid gets sent to a different matrix. And so we can, if we want to study different braids, they have different matrices that go along with them. And so I mainly answer questions about this sort of translation process, not so much about the braids themselves, but about the process by which we're translating them into this other object. And so faithfulness is kind of the major motivating question that I study.
So the idea is that you have this kind of a very concrete but slightly less rigid object, like a braid, and you're trying to find some way that you can change it into a way that's easier to deal with, but doesn't lose any information about the original braid?
Exactly. So a faithful representation is one where we didn't lose any information. Any property we would want to study about the braids, we can then study in these matrices instead, and we didn't lose any information.
So presumably you're not studying braids because there's a well-funded hair braiding industry out there that's looking for new information on their craft. So what sort of questions are braids used to answer in mathematics?
Oh, all sorts of things. I would say maybe an interesting application or a way that braids are used is a motivation coming not from mathematics, but from physics. So quantum computing is sort of a really hot topic right now. People are trying to build quantum computers, and this is very different from, the classical computers that we're zooming through right now. It would be a totally different way of computing and creating electronics, or using electronics to do computation. And one way to model a quantum computer is actually to use braids. And it's a very complicated physical setup that I don't really understand. I'm not a physicist, but the sort of basic idea is there are these little tiny particles that are called anyons, and they live in this very flat, like two-dimensional world, and they're very sensitive. So if you rotate the particles around each other, the particles sort of remember that rotation. So they're sort of linked in a way. And so if you take these particles and you rotate them around each other and swap them and swap them and swap them, over time, what you're doing is you're drawing a braid that's sort of remembering how you were swapping these particles around. And so that braid that you're drawing is a way to model the computation that you did by swapping the particles. And so there's this thing called topological quantum computing, and the model for that is these braids. And so there's a lot of work being done to try to understand what types of computations you can do with these braids, and how good is this model of this computation. And so that's sort of using mathematics to give like a model for this physical situation that they're using to create this computation. And so I think that's a really exciting application of braiding in a way that, is not at all obvious when you first think about a braid and how can a braid be used to study the world. So I think it's pretty exciting.
What sort of things are you looking for? Are you going for the problems that look interesting, or the problems that look beautiful, or the problems that look simple, or the problems that look really hard? What attracts you to a problem?
Well, I'm at the stage in my career, so I just finished my PhD a year ago, and I'm kind of in my postdoc years. And so when I choose research problems, I kind of have several agendas. So one, I have to choose problems that are interesting. But two, there's very much a push for me to publish. Like I'm going to be, when I'm looking for my sort of permanent career as a tenure track professor someday, I will be judged on how many papers I have published. And so part of what I have to do is pick problems that are interesting, but also that are solvable, that I think I can do with my skill set and kind of the stage of my career I'm in. And so the sort of questions I find interesting is even though I live in the world of topology and algebra, I'm typically drawn to more algebraic solutions to problems. And so what that might mean is instead of drawing a picture of why something is true, I prefer like manipulating formulas to show why something is true. And I find those answers to be like a little more satisfying.
So you're just out of your PhD a year ago. So this makes you what we would call an early career researcher. Can I ask, what is life as an early career researcher in mathematics like?
It's definitely a balancing act. So I think for me, as a visiting assistant professor at Wake Forest, I've had to teach quite a hefty load in addition to doing research. So I've had to balance teaching and research, which I really love teaching. So it's been a pleasure, but there's been a lot of demands on my time. And so I think a big challenge has been just balancing all the different responsibilities that I have and sort of making sure I get the daily tasks done as well as the sort of longer term research tasks. And I think the hardest part about being a new researcher is coming up with new projects. So when I did my PhD, my advisor had a project in mind. And while I pushed it further than my advisor had planned, I still was not the one who generated that project. And so the new skill I'm having to learn now is how to generate my own projects. And it's very difficult to determine how hard a project will be. Because some things are, not provable. And so how do you determine a not provable thing to something that might take a few weeks to prove, to something that might take 10 years to prove? And so, there's a lot of new skills about how to conduct research in addition to, or taking into account all of the sort of pressures of the job.
How do you do that? I think different mathematicians have different ways that they like to work. what way do you find that is most successful, most fun for you?
I love to collaborate. I do not like to do math alone. I find it very lonely. I like to seek out other mathematicians who are interested in the same types of projects that I am, hopefully who have different sorts of skill sets so we can kind of come together to solve problems that we couldn't do on our own. So my purpose of coming to Sydney was to work with Dr. Zhuzhana Dancho, and she and I not only have complementary mathematical skills and interests, but as far as our like life outside of math, we have a lot of other common interests. And so she's someone I love to work with because we can like go to work together and have fun, and then after work we can have fun, and it makes math so much more fun.
So you said that with your collaborators, you also talk about your interests outside of mathematics. You seem to have quite a large selection of interests. In particular, you competed in the Dance Your PhD competition, and you made a dance video about your mathematical research. Can you tell me a little bit about that?
Yeah, so I have been a dancer my whole life. In fact, like until I was 18 or so, I thought I was going to be a singer and a dancer on Broadway. That was like what I wanted to do. And then I found mathematics, and my life went in a different direction. But I love performing. I love dancing. I love being on the stage. And until a couple years ago, math and dance were just very separate parts of my life. But Science Magazine puts on the Dance Your PhD competition every year. And I think it's been going for about 11 years now, 11 or 12. And this competition is for graduate students internationally in the STEM fields to make, and the challenge, the competition is to make a dance video about your research. And the only rule of the competition is the person who's the graduate student has to appear in the video, has to be one of the dancers. And so I had heard of this competition, and they don't often get many mathematical videos submitted to this competition because it is very difficult to blend math and dance. But when I was in grad school, I joined an aerial dance performance troupe. And a friend of mine was like, Nancy, you do research in knot theory, and you are like tying knots with your body in the air every day after work for fun. Like, you have to make a dance video about your research and submit it to this competition. And I was like, you're right, I should. This is a great idea. And so, so one summer, a couple years ago, I think it was 2017, I would just like gave myself permission to think about, okay, if I were to make a dance video about math, if it were not impossible, what would I do? And then once I sort of gave myself that permission, then I was just like exploding with ideas. And part of what I found was a lot of the language that mathematicians use to describe math to each other, sort of more casually, not so much like, when we write an official research paper, but the way that we discuss it verbally, we often use a lot of words of movement. And we often describe, that the objects that we're working with as like, oh, this person goes over here and this person gets flipped around twice. And so I started to think about the language that mathematicians use. And then I started to see like the movement and descriptions of movement. And then just, you just let your imagination run with it, and all sorts of ideas will come to you. So I ended up making an aerial dance video about my research, and I won the competition. So that was really exciting. And my career has been forever changed. Like, I will always be thinking about how can I turn my research into dance, and that will just always be an avenue of my work.
So you've that wasn't the only project that you did. You've done some more since, correct?
Mm-hmm. Yeah. So the main sort of medium that I use is video, but I have done a few live performances where I sort of gave a lecture about knot theory while I was dancing. So I had I had a little like remote control in my hand, and then I had a slideshow going, and I would like climb up into the aerial silks and describe some sort of mathematical content, and then I would do it with my body in the silk. That was pretty fun, but very technically challenging, and I'm out of breath a lot when you're like climbing up. So I found that doing live performances is a little taxing. But I did make another video And this was for another competition put on by the National Science Foundation in the US. And they made a competition that was just to make a video kind of describing your research. And I won honorable mention in that competition. So that was exciting. And in that video, I wasn't describing my research so much, but I was more trying to describe how there are different fields of mathematics. And so you often hear, or like even I've described today, about algebra and topology, geometry, and there's all a slew of different types of fields of research in mathematics. And in my experience, when I talk to people who are not mathematicians, it's not so clear, it's not well known what those different fields are and how there can be different fields of mathematics. So I made a little dance video trying to describe how these fields are different.
Do you know a lot of other mathematicians who are dancers or in the performance arts as well as mathematics?
More than you might think. So when I won the Dancer PhD competition, my video kind of went viral, and I was contacted by mathematicians all over the world. They'd send me an email or find me on Facebook or something saying like, I'm also a dancer and a mathematician. This is great. And I just had no idea that there were so many math dancers around.
All right. Well, thank you very much for your time. And I hope that we get to see you here in Sydney as soon as they allow international travel again.
Me too.